We'll continue with our lesson on thermodynamics today. This is all fitting into Big Idea 5, which is very broad in nature, but in your review books, which you were given prior to break, you'll be looking in Big Idea 5 for these types of problems. So you want to be able to use the laws of thermodynamics. We talked about the first law of thermodynamics yesterday to describe the essential role of energy and explain and predict the direction of changes in matter. And you'll see more of that as we work through both this chapter as well as chapter 17. We're going to pick up today with calorimetry, which allows you to measure quantities of heat. You will be doing a lab next week designing hand warmers where you will be using calorimeters. And calorimeters really are very, very simple. You can have fancy ones, or you can essentially have two nested styrofoam cups. You want a lid to reduce the loss of heat or energy from your system, a thermometer to measure temperature, a stirrer so you can continually stir the solution, although we will be using stir plates with stir bars, and that makes it a little bit easier to stir or mix the particular solution. But a nested styrofoam cup. Calorimetry allows you to measure quantities of heat. You can measure things such as specific heat. You can measure heats of fusion, heats of vaporization, etc. We're going to look right now more at heat capacity as well as specific heat. I mentioned heat capacity here. It does come up a little bit on the exam as well as on your lab. You'll be determining heat capacity of your calorimeters to get the lab going before you look at reagents that would be most effective in hand warmer design. We already know that the law of conservation of energy says that any heat lost by the system is gained by the surroundings, or vice versa, depending on whether it's exo or endothermic. Heat capacity is abbreviated with a capital C. Be careful there. Heat capacity, capital C, specific heat, lowercase c. So clear handwriting here so that you don't have an issue. This is the quantity of heat required to change the temperature. Change in temperature is delta T of the system by 1 degree Celsius. It depends on the quantity as well as the type of matter, and it is calculated. Heat capacity is equal to heat divided by the change in temperature, and the change in temperature is the final temperature minus the initial. So if your experiment has an initial temperature of 30 degrees Celsius and your final temperature is 50 degrees Celsius, your delta T will be 20 degrees Celsius. So if it's warming, delta T will be positive, and if it's cooling, delta T will be negative. In the first example, it says calculate the heat capacity, so you're looking for C, of brake fluid if the sample must absorb 911 joules of heat. That's the Q. The unit for Q is typically going to be joules, although it could be in kilojoules, and you'll make a conversion. 1 kilojoule is 1,000 or 10 to the third joules. We'll scribble that down in a sec. For its temperature to rise from 15 to 100 degrees Celsius. So let's take a look at this one in a little more detail, just so it's clear to you. We want to know the heat capacity. That's what we're looking for. The Q is 911 joules. The initial temperature is 15 degrees Celsius. The final temperature is 100 degrees Celsius. Remember, when you add or subtract in regard to sig figs, it's the least number of decimal places. So that will be 85 degrees Celsius as your delta T, final minus initial, if you haven't looked at temperature changes in the past. we know that the heat capacity is equal to Q over delta T, and that's going to be 911 joules over delta T, 85 degrees Celsius, and that's going to be 11 joules per degree Celsius. So note the unit for heat capacity, capital C, and that unit is joule per degree Celsius. You'll see heat capacity in your lab. You could see it in an AP type question, although typically what you're probably more familiar with from honors is specific heat. Very similar, but it's the heat capacity of a 1 gram sample. So to go from heat capacity to specific heat, you simply divide the heat capacity by the mass of your sample, and that's what you see here. Specific heat is the heat capacity of a 1 gram sample. We're going to divide the heat capacity by the mass, and ultimately you derive this equation shown here. Q is equal to MC delta T. Q is the heat transferred. Sometimes it'll say energy. M for mass in grams. C is specific heat. Specific heats will be provided to you. Thank you. And the unit for specific heat will be joules per gram degree Celsius. We'll write that out in just a sec. I just want to make you aware of the formulas that are provided to you on the AP exam. So in your thermodynamics section, you're given Q is equal to MC delta T, and they do provide you with those abbreviations for the variables or the variable designation. We saw this formula the other day, so that is provided to you. Some of you are familiar with entropy and free energy already. All of these formulas are provided to you, so you don't have to memorize them. However, I have seen it given to you with heat capacity instead of specific heat. So just be aware this is given to you. This is not, but your units will always drive you in the correct direction when solving a problem. So watch those units, because a few years ago, and we'll take a look at one of the questions, I think it was on the 2015 exam, they really needed this instead of this, and a lot of the kids couldn't get there. So just be aware that it is very easy, and the units you'll see in the problem will drive you toward the correct answer if you can focus on them. And it is tricky when you take an exam, especially one of this magnitude, because there is a lot of pressure. All right, as we said the other day, when heat is lost by the system, Q is negative. Exothermic, when heat is gained by the system, it's absorbed, Q is positive. So in this example here, there are a few of them, and we can work through them slowly. I have it all written out for you, but we can work through it from scratch. It says what mass of water, and let's pull those variables out. You have that already, but maybe you want to scribble a few things down so that you can see the whole derivation. The question says what mass of water, so we're looking for the mass of water, can be heated from, so the initial temperature is 5.5 degrees Celsius. The final temperature is 55.5 degrees Celsius, and it indicates that your heat is 836 joules. The specific heat of water is provided to you. at 4.18 joules per gram degree Celsius. Sometimes it'll be given at 4.2. Don't be upset if they have units in kilojoules. Just make sure they're consistent. We know Q is equal to MC delta T. To solve for mass, we're going to divide both sides by C delta T, and that's a lowercase c. So mass is equal to Q over C delta T, and you've got 836 joules divided by 4.18 joules per gram degree Celsius times your delta T. So that's going to be 50 degrees Celsius cancel, joules cancel, gram is in the denominator of a denominator, flipping it to the numerator, and you've got 4 grams of water. And again, really just requires a little practice, nothing really doing there.
Sorry, so the T with the little I, that's the
Initial, and T final is final. This, I guess, should have a little dot. Sometimes they do T1, T2, but usually TI, TF. The other problem is a little bit trickier, but nothing that you wouldn't be able to handle. You've got it all worked out there for you. I'm going to go back through because there's a few things I want to point out. In the second example, it says that you have a 454 gram block of lead. The initial temperature, TI, is 22.5 degrees Celsius. We want to know the final temperature when 400.22 kilojoules of heat is absorbed. The specific heat is 0.128, joules per gram degrees Celsius. And that's provided to you. If you're ever looking for the initial or the final temperature, your formula is Q is equal to MC delta T. I would solve for delta T first. So delta T is equal to Q over MC. And once I got the delta T, then I would solve for the other component in a separate step. I wouldn't make it algebraically complicated because it doesn't need to be. In addition, your unit for C is joules per gram degree Celsius. In order to get the units to cancel, you've got to have joules for both or kilojoules for both. So you're going to multiply this by 10 to the third or move the decimal 3 to the right, whatever's easier for you. But make sure you have the same units or you are going to have a mess. 4.22 times 10 to the third joules. The mass is 454 grams. The specific heat is 0.128 joules per gram degree Celsius. That's why it's so important to include units everywhere. Your delta T is 72.6 degrees Celsius. But that's not what they asked for. They asked for the final. So you know that delta T is equal to T final minus T initial. T initial is given, you're looking for T final. You would add T initial to both sides. I'll add the quantity here. And the sum of the two is 95.1 degrees Celsius. I know that's really low. I can't even seem to get the thing to go all the way. So 95.1 degrees Celsius. And again, I can't emphasize enough the importance of doing many of these problems at home tonight and or tomorrow night so that you master this concept prior to your next class. Really important.
Sorry, what is Q and C?
Q is the heat. That should be in your notes.
Yeah, it probably is.
No, maybe it isn't. Here, let's write it in. This actually, did you not do Q is equal to MC delta T in honors last year?
No.
Nothing? Okay. So Q we've given prior, but Q is heat.
It's on the first page.
Yeah, I would think so. C is specific heat. M is mass. And delta T is the temperature change. And that's always going to be T final minus T initial. No problem. The other type of thing you can do with calorimeters is you can measure specific heats, and typically what you do in this particular instance, I'm not going to read all that, let's just draw it out, is typically what you're going to have is a calorimeter. In the calorimeter will be the water. You will know the mass. You know the specific heat of water, or it will be given. You will know the initial temperature of the water. Into that, you will drop some unknown substance, often a metal. You will know the mass. You will be looking for the specific heat. You will know the initial temperature. You also, of course, need a thermometer so that you can measure temperature change. And some type of stirring apparatus, usually a stir bar, and it's on a stir plate. I won't draw it all in. What's going to happen when you drop a hot substance into cool water? The water is going to absorb the heat lost by the unknown substance. And ultimately, the temperature will stop changing. This will be the final temperature for both. If you have the final temperature for both and the initial temperature for each one, can you get the change in temperature? Sure, you just subtract. Now, the water is warming, so its final temperature will be greater than the initial temperature. Its delta T will be positive. The substance is cooling, so its final temperature is going to be less than its initial. So will this delta T be positive or negative? Negative. The Q for the unknown substance will be negative. The Q for the known water substance, which starts out cooler, will be positive. What can you say about these two Qs? What do you know about the conservation of energy? Right, so any heat lost by one substance is gained by the other. So these two quantities will be equal but opposite in sign. And as a result, you can work through. Essentially, everything written out is in my drawing or in the explanation. The example states a 23.9 gram piece of iridium is heated to. So the mass of the iridium is 23.9 grams. And the initial temperature of that substance is 89.7 degrees Celsius. It's placed in a calorimeter, so this is going to be for the water. The mass of the water is 20 grams. The temperature of the water rises from, so the initial temperature is 20.1 degrees Celsius, and the final temperature is 22.6 degrees Celsius. We want to calculate the specific heat of the iridium. Sometimes you are determining the specific heat of an unknown substance, and once you get the specific heat, you compare it to a table to figure out what the substance is. The way I go about these problems is a three-step procedure. In step one, I'm going to calculate the Q for the water. I know for Q of water, I've got MC delta T. The mass of the water is 20 grams. The specific heat of the water, which will be given to you, is 4.18 joules per gram degree Celsius. How do we get delta T for the water?
You add the T of F. Oh, no. Yeah, you subtract the T of F. I mean the T of I from T of F.
You got it. So TF minus TI is 2.5 degrees Celsius. So I have 20 times 4.18 times 2.5, and that is 209 joules. Be careful here. This should actually be 210 joules because you got down to 2 sig figs here. When you subtract, you go to the least number of decimal places. Now in step two, this one's really easy. We know that any heat gained by the water is equal to heat lost by the metal. They are equal but opposite in sign. So the Q of the iridium is negative 210 joules. These will be equal but opposite in sign.
I missed that. Why did you write 209?
Because you only need 2 sig figs. You have 2 sig figs here after you subtract because you maintain the decimal place to the 10th. And so now you have 2 sig figs, so I got it to 2 sig figs here. And then finally, in step 3, you're going to calculate the specific heat of the iridium or unknown substance. We know that Q is equal to MC delta T. So, and usually on a lowercase c, I'll make it script sometimes so that it's easier to follow. So specific heat is equal to Q of the metal over M delta T, all for the iridium. Be careful, negative 210 joules. The mass of iridium is 23.9 grams. How do we get the delta T for the iridium?
I need like the delta T of the whole solution itself, like the water and the three.
Jason, what do you got?
Give me a second. Stretching.
I know, but he knows how to do it. How do you get the delta T for the iridium? What do you know?
I have to calculate it. Don't we have to use the formula with the grams and the and reverse it?
Go ahead.
The TF from water minus the TF from the metal.
Why can you use the TF from the water?
Use the T for both.
Exactly. So, you're going to use the final temperature, because that's for both, minus the initial temperature here. So to get the delta T for the iridium, you're going to have 22.6 minus 89.7, and that's negative 67.1 degrees Celsius. The negatives are going to cancel. You can't get a negative specific heat. Be careful there. And the specific heat is 0.13 joules over grams degrees Celsius. Yep.
Are we ever going to have to do a question where we don't know what metal we have?
You could, but you would be given, you would calculate the specific heat in the exact same way, and then you would be given a table and you would just match the quantity. And some of you this should look very familiar. For others, I know it's brand new. For all of you, 3 problems like this tonight, you'll have it cold.
So the final temperature is the same for both things, and then for Q, whatever you decide is the opposite for the other.
You got it. On your practice quiz, I'm going to pull it up here. There must be a good comparative type question that I would like to explore. And this is where it can get a little bit tricky, and I'll give you your practice quizzes out today. On number 10, let's take a look. It says, consider for 100 gram samples of water, each in a separate beaker at 25 degrees Celsius. Into each beaker, you drop 10 grams of a different metal that has been heated to 95 degrees Celsius. Assuming no heat loss to the surroundings, which water sample will have the lowest final temperature. And actually, some of you may have trouble reading off the screen. And be careful in your practice quiz. You're going to have 2 part 3s on here for 2 different chapters. So it's going to be on the last inside page. I'll hand it out backwards so you can just flip it and it might be easier for you to see. Take a minute, scribble a few ideas down, but this is where it can get very tricky. You want to make sure that you can work through these problems. And this way you can scribble it right on there. Remember what I said, open it up to the last page. I didn't number the page there. But it's on, if this, the way I handed it out, if you just go like this, the question's right there in between the lines. Give it a shot. Oh, I could have sworn I did 5. Josh, was there one left or no? Okay, here you go. I counted you, I just didn't count the sheets. I'm sorry. Give it a shot. I gotta scribble too. See what you can cancel to make it easier. What do you think? How do we approach it?
Can you eliminate B and C?
Can you eliminate what?
B and C,
Why?
because their values are in between the 2 other numbers. So it would have to be either the highest number or the lowest.
Good strategy.
And because it's asking for lowest final temperature, I chose the one with the lowest value.
Why?
Okay, so that would be Q that we're given?
Well, we
No,
have
no,
Q
that's
is
not Q,
equal to
that's-
MC delta T, and we want to basically set them equal to one another, where this can be the metal and this can be the water. Now, what can you dump? What stays the same for each sample? The masses. So get rid of that. All right? So now you've got specific heat of metal, delta T of metal, specific heat of water, delta T here. So what are you going to do?
Isn't delta T and C
They would be inversely related because they're multiplied to one another.
So then it would be the highest one?
But you got to think it through. Delta T is final minus initial, correct?
Yeah. Oh, that would be the initial.
What are we going to do? Come on, I've got 19 brilliant kids in here. Somebody come up with something super brilliant. You can do it. Think it through. It's going to help you for your quiz, for the AP exam. You know these variables are inversely related, but you also want to think about it this way. When we went back to our previous question, how did the delta T of water compare with that of the metal?
Or not the same, but negative of, like,
Not the delta T's. Comparing the absolute values of these, you can see that the change in temperature for the metal is quite large. Right? Okay. Also, take a look at the specific heat for a metal versus the specific heat for water. The specific heat of water is quite large, hence the small delta T. Correct? Okay. Now, they're not just asking about delta T though. In terms of water then, we know delta T is going to be relatively small. Do you get a small delta T with a lower or a higher final temperature?
Lower than water.
Okay. So what's going to have the lowest final temperature?
aluminum, because its specific heat is larger than that of lead, and since lead has a low specific heat, it retains heat, or it doesn't retain heat, but it absorbs heat much easier, but it doesn't retain it as well.
Explain it mathematically.
So,
Make it really simple. So you want to go with something big here. Which means something little here. Correct? And if it's something little here, then the final temperature of the metal would be low, giving rise to large delta T for the water. But that's not what we want. We want a small delta T for the water. And in order to get a small delta T for the water, that does this. So what would your answer be?
lead,
Why?
That was right.
it has a lower specific heat, and because it has a lower specific heat, it can absorb more heat.
And that is true. And you just, see, I work things out mathematically because it's easier for me. So you had an idea, but if you follow through here, then your conceptual idea will explain it mathematically, and I think it'll be easier for you. And yes, your guess was correct, but make sure you understand the reasoning. So in this particular instances, the water sample that will have the lowest final temperature will be the one with the lead that had the smallest specific heat, because with that smaller specific heat, you will have a larger delta T for the metal which indicates a lower final temperature for both. So it's a little bit tricky. Okay? Excellent approaches in regard to eliminating B and C. In this particular instance, I think mathematically you would be stronger in this regard. I would highly recommend that you take a look at those types of questions. We'll take a look at energy changes involving a change of state. We'll look through an example from an AP exam. This was the one I was referring to, as well as Hess's law next time. All right? Energy changes that accompany different chemical reactions.